right, so this is going to be our first set of lecture, I suppose, for the second semester for our 2021 part of the school year. So if you wanted to follow along in your textbook, which I strongly encourage you guys to do because the book gives all of this information in another style, another version. They provide practice problems and examples and all sorts of great stuff that I really strongly encourage you guys to check out. You can find all of this information in your textbook in Chapter 9. So for us, Unit 8 is impulse and momentum. And this entire unit, I like to start second semester with this unit because it's not a brand new concept in terms of the pieces that make it up. All of the variables that we're going to talk about that we use to calculate momentum are already variables that we've discussed extensively in first semester, right? So we're stepping away from gravity and we're not doing any circular motion sort of stuff. We'll come back to that when we do waves later, but we are going to get back to masses and velocities and force and time and all of that good stuff that we talked about first semester as an application for describing momentum, a word or a phrase that a lot of you tried to use occasionally during first semester because it's something that we've all heard being used and probably know a version of a definition or application of it from everyday life. Describing things as having some sort of momentum while you might not do it every day isn't something that would be totally foreign to you. You've got some sort of background to it. So we're going to take what little background you might have of it, along with all of the variables we discussed from first semester. If you check out the unit packet cover page for Unit 8, you'll see at the bottom of that packet, the cover page, all of the variables. The first 4 variables are things we've already talked about. You've got mass, velocity, time, and force. Those are the pieces that make up momentum and make up impulse. So we're going to talk about those. And the idea is that actually this goes back to Newton yet again. It's kind of a big deal a couple hundred years ago, but it still is. Newton, when he wrote his laws of motion, the 3 laws of motion that we have already studied, primarily his second law, F equals ma, he didn't actually write it in terms of an acceleration. It was an application that we came up with shortly thereafter. He described forces as causing a change in velocity. Now, we know that change in velocity we now call an acceleration, right? You can speed up, you can slow down, you can turn and change direction because that's part of velocity. But those forces cause some sort of acceleration. That's where F equals ma comes from. Newton would have written it out as, F is equal to mass multiplied by your change in velocity over time. That's actually how he wrote it, but we're going to work with that a little bit more. So we're actually going to step away from using the term acceleration. If we want to use acceleration when we're talking about momentum or we're talking about these more complicated concepts, we would have to talk about g-forces, which you might have heard about if you're interested in spaceflight or piloting in general. It's a rating of how many times greater the forces on your body are than the force of gravity. It would probably also involve at some point calculus, and we're obviously not going to do calculus in this class. So we take a step back from acceleration in this particular unit. We talk about velocity. How do forces affect velocity? And we know that acceleration is a change in velocity over time, and we know that forces can cause changes in those accelerations. So with a little bit of substitution from your 8th grade or 9th grade math class, we can rearrange all of this to get one final new-ish equation. This new-ish equation right here in red is the equation we're going to be using from time to time throughout the course of this unit. And the whole next slide deals with it. But there are a couple of things that I want to point out now that you understand where we're going, right? We're talking about how forces impact changes in speed. That's this unit, right? How do forces affect momentum, really? And to do so, with at least these notes, one of the things I would encourage you guys to do, if you're copying any of this down, don't sit there, please, and write down everything that I have on the entire screen. The stuff I put in red, for those of you who missed this first semester, didn't pay attention, or just weren't here because you've just joined us, the things I put in red are things that I would have written down in my notebook. as main ideas from these slides, right? You don't have to copy every word verbatim. You don't have to have this entire proof going from A equals V over T and F equals MA, showing the substitution and moving time over to the other side of the equal sign. You don't have to show that. This right here was the end result. And that's the important part. That's what we're starting the next slide with. So there's my equation, the same equation up top. It is force multiplied by your change in time is equal to your mass multiplied by your change in velocity. All of this came from F equals ma. Right? That was the point of the last slide. Now, each side of this equation tells us something different and something really, really, really important. The left side of this equation, that force multiplied by time, is actually a term that we describe as impulse. I like to think of impulse because it's a phrase that you probably haven't heard of. It's not something you have a lot of schema or background on. Impulse for me is like the impact. Right? When two things collide, when two things run into each other, when two things exert forces on one another, it is the result or the experience of that impact of those two objects. How much force is applied and how long is that force applied for? Now, it's measured in a unit of Newton seconds, right? Not Newton per second. You're doing Newton's multiplied by seconds. But that's what impulse is. It's how much force is applied and how long that force is applied for. And if we go back to Newton's second law, F equals ma, using this rearrangement we have at the top of the screen, you'll notice that it's equal to something else. Impulse can be the same as, and what we have over here, I'll do a little squiggly so that it's different, right? You've got impulse and you've got momentum. The right-hand side of that equation describes momentum. If you want an equation for momentum by itself, it's P equals mv. Now, I, for years, have asked everyone smarter than me that I come across why on earth we use P for momentum, and I have not got a good response. It's not like, potassium is K on the periodic table and sodium is Na because it comes from the Latin roots of those words. Everyone I've asked just kind of shrugs and says, oh, it's the way it's always been. And I hate that, but I don't have a better answer. So maybe there's too many M's, right? You've got meters, you've got the prefix milli, you've got, mass. And for some reason, they use P for momentum. It's a capital P. Don't know if that changes things for you. It makes it less weird, but it's still pretty weird in my opinion. But the point behind this is that we took an equation we started with that we knew, F equals ma, Newton's second law, and all we did was change acceleration to be the equation that it would have been, using velocity and time, the same equation we would have used back in Unit 2 to solve for acceleration, and rearrange that equation. All of this still stems from Newton's second law, and what it tells us is that the force applied to an object and how long that force is applied is equal to how much the momentum of the object changes by. And that is the impulse momentum theorem. All right, the impulse on an object is equal to how much its momentum will change by. If you exert a force on an object, you're going to change its momentum. You're going to cause it to change its motion, to accelerate, speed up, slow down, turn, whatever. It's going to change what it was doing, right? Newton's first law, things in motion will stay in motion unless acted upon by an outside force. Well, how much does that force cause it to change? That's his second law. And this was an application of that. So that left-hand side, your impulse tells you how much your momentum will change by. If you have a positive impulse, then you'll have more momentum, you'll gain momentum. If you have a negative impulse, you'll lose momentum, right? You're either speeding up or slowing down. Those things haven't changed. We're just assigning impulse and momentum as the words we use to describe them here. But it's the same concepts that we've had before. And that was the point. Now, there's going to be, and this is the hardest part for students, you don't have to write down any of this in blue. There are any number of ways that you can write out this impulse momentum theorem, right? This idea that forces cause changes in speed. The one I'll write most often is I equals delta P. Remember that letter delta just means change in. And that's the one I'll write most often because it involves the least amount of writing. I don't hate myself and I'd like to write as little as I possibly can. But the impulse momentum theorem can simply be written as I equals delta P. Or if you don't like the Greek letter delta, meaning final minus initial, you can rewrite it the way it is right next to that, right? I equals final momentum minus initial momentum, because that's what delta has always meant. Or you could rewrite impulse as what made up impulse, and that was a force multiplied by time, is still equal to your change in momentum. Or you could write both of them out separately, or if I'm being completely honest, you could get a little bit more complicated, and you could even say, this is one of them I'll encourage you guys to do at some point. Here's my impulse, and my change in momentum is my final mass multiplied by final velocity, because that's how I would calculate momentum. It's mass multiplied by velocity, minus, not plus. Just make it a bigger minus sign, minus your initial velocity, giving you your initial momentum, right? And we're going to work through all of this. I'm going to kind of do what I did with the last unit since we're still remote. I'm going to give you every possible example that you could ever see throughout the course of this unit in this set of notes using these equations. That way, when we're doing the homework, you have an example already worked out, right? The book has several examples already worked out. You would just have to go back through and read them. But I'm going to give you even more, and I want you to use them as a reference when we're going and doing the homework. So that's the idea. So so long as you understand that impulse is responsible for changes in momentum, responsible for changes in speed, that force being applied over a certain amount of time is responsible for that thing to change its motion, we're good. That's the impulse momentum theorem. Our first example, honestly, I'll walk through them a little bit. This is assignment 1. This is the one I want you guys doing for homework. You'll see that on the calendar. It's due Friday, the 8th at midnight on Teams, just like all the other homework assignments always have been. And if I'm being completely honest, if you're watching this video, you're welcome. All of the answers are here, right? I'll walk through not all of them, but I will do a good amount of them with you. I don't want you to just copy them. I understand that some of you probably will. It's not going to benefit you in the long run. And as long as we have that understanding from here, you do what it is you feel like you need to do. But I do want you to give them a shot, right? And I'm going to walk you through a couple of examples where we identify variables, draw a picture maybe, and kind of take those steps together at the beginning for the first couple of examples. And then the point behind giving you all of the work for all of the problems on here was to give you a place to come back and check your work so that you could see where you might have missed a step and ask some really good questions as we progress. It'll be 2 weeks before I see you guys. And so I want to give you guys as many opportunities to ask as many questions and be as informed as we can be before we come back. So example number 1, this is from assignment 1. This is part of the homework, so here we go. A compact car has a mass of 725 kilograms. Right off the bat, we should know that we can label that with a letter M because that's a mass. And then we've got a velocity. This is not an acceleration. 32 meters per second is always a velocity. Take a look at that data table that we made first semester of all of the units, the symbols we used to describe those, all the variables, the symbols we used to describe those variables and the units that they contain, and you'll see meters per second is always a velocity every single time. And so letter A in example number 1 asked you to solve for momentum. So this is my real quick simple equation for momentum. I picked this one because it didn't ask for impulse, it didn't give me a force, it didn't provide me with any amount of time, right? All I've got is a mass and a velocity. We plug it in here and notice how quick and easy this is. Now the units are annoying, right? In last semester, when we did F equals ma, force is equal to mass multiplied by acceleration, our units actually came out to be a kilogram meter per second squared because it was units of mass multiplied by units of acceleration. And scientists, physicists, over the decades following Newton's death decided that was a really silly thing to say again and again and again and again. So they named that kilogram meter per second squared a Newton in honor of the late Isaac Newton, who did all of this pioneering research and invented calculus that allowed us to do all of this mathematics and apply it to the universe and make it a lot less mysterious, but way more cool. So that's what we did. We did not do that with momentum. I don't know why we didn't do that with momentum. We just didn't. So I'll often, just because it's annoying to say, I'll say we have 23,200 units of momentum. That unit is a kilogram meter per second. It's mass multiplied by velocity. But I'll often just, when I'm talking real quickly in class, I'll just say, 23,200 units of momentum, because it's easier than kilogram meter per second every single time. No, it's just a personal thing. But those are the units. A second car has a mass of significantly larger value, 2,175, moving at the exact same quantity of momentum. It has the exact same amount of motion. Now, it's more massive. So in order to achieve the same amount of momentum, it doesn't need to be moving as quickly. Right? It's one of those old adages. I played football for a decade, so I always like to liken it to that, or hockey, or any other contact sport. If you're small and you want to hit someone hard, you got to be going fast. But if you're big and you want to hit someone hard, you don't have to be going as fast. Right? You can generate the same momentum with less speed. And all of that comes back to, obviously, our equation. And we're going to use our equation. A lot of the equations that we'll start with in this unit will be this quick, this simple. Calculate the amount of momentum. Here's the thing's mass. Here's the velocity. Or here's the amount of momentum it has. Divide by the mass to get your velocity. And that's all these first couple need to be. So there was number one for you on the homework for Friday. It's not meant to be terribly complicated. Not yet. It will get a little bit more complicated, but trust me, we're going to take it slow and we'll walk it through it. Example number 2. This is where I'm stepping away from momentum and looking a little bit more at impulse, right? You see newtons, right? 5.0 times 10 to the third newtons and a number of time, 2 seconds. So obviously we can't use P equals mv because none of those are a force and none of those are a time. So the driver of a compact car in the previous problem, we can still use it, same mass and velocity, I suppose, if we wanted to, hits the brakes for 2 seconds, applying a force of 5,000 newtons on the car. What is the car's change in momentum? What is its impulse? Remember, those two things are the same. So we can calculate its impulse using I equals Ft, force multiplied by that amount of time. And remember, in this particular case, it is a braking force, so it did have to be a negative 5,000. And I'll talk more about that later when we get into direction and how direction is a little bit more important later on. Either way, the impulse experienced by the car would be described as negative 10,000 newton seconds. Again, units of impulse, it's just a force multiplied by time. How much force and how long was it applied for? That negative 10,000 is responsible for the car slowing down because that's what happens when you hit the brake, right? You have to apply that negative force for a certain amount of time. Determine the new velocity of the car after the brakes were applied for those 2 seconds. Well, this is one of those cool things that we can do. If you've got a force in time and you can find your impulse, you know your change of momentum. That is your impulse momentum theorem. The two are equal. Always. And that came from Newton's second law, right? That was the whole, there was the title slide, and then the first official slide here was F equals ma. Let's convert it into Ft equals mvf, m delta v. And it showed the relationship between impulse and momentum. And so we can just take that negative 10,000, plug it in. Now, be careful here with the mathematics. If we want to find our change in momentum, it's final minus initial, sure. We don't yet know, and this is what we're solving for, the new final velocity of the car. The mass of the car doesn't change. It's still 725 kilograms, but its speed was 32 meters per second when we started. Then we hit the brakes, applied this amount of change of momentum, that amount of impulse, and we're going to have some new speed. That should be slower. We hit the brakes. This should be less than 32. If you get a number that's greater than 32, please ask me, any number of questions. But the one thing I will mention, make sure you deal with this side first, right? The 725 and 32. Multiply those and then add them to both sides. And then once you've added them to both sides, because again, this is just reverse order of operations, just like 8th grade, 9th grade, whatever it was we were doing algebra introductions for. Then you divide by 725 and you get 18.2. It is indeed less, right? It's a slower speed, which makes perfect sense. You hit the brakes, your car should slow down. If you hit the brakes and your car speeds up, something has gone catastrophically wrong, and I wish you the best of luck. So you can always do those quick common sense double checks here with this class, or especially this unit. So why do we care? That's the overarching big question after I introduce impulse and momentum. It's a multitude of reasons, but I would argue the most important, the main idea of those first several slides, outside of the equations, obviously, those are important, is that forces cause changes in speed. right? Forces cause things to accelerate. We're coming back to Unit 5. This was first semester stuff. But we've got a new way of describing how that force causes a change in speed, right? We don't have to talk about acceleration because accelerations are weird. But what we can use this for is probably one of the best real-life experiences that we'll ever come across that no one ever wants to be involved in, hopefully. If you want to be involved in one of these, we should probably get some sort of help. But no one wants to be, ideally, in car crashes, right? They're oftentimes, quick little fender benders. They suck. You got to deal with insurance. And then if they get worse than that, then you have to deal with hospitals and ambulances and hoping everyone is okay. And no one likes them. But they are a fantastic example and probably one of the most widely used examples in physics for impulse momentum theorem, how forces can affect changes in velocity, right? If you like your CSI shows and stuff like that, this is literally what they do when they investigate those car crashes or those crime scenes. So in a bad car crash, we're going to go with the worst possible case scenario right off the bat. You're probably going around 65 miles an hour because you're doing the speed limit on I-80 like no one does. And let's say you go from that speed on I-80 to darn near zero as our worst case scenario. Let's say you do that really, really, really quickly. This impulse momentum theorem can help us describe how much force will be exerted on your body. And we'll get to why this is important later. So assuming it's a perfectly elastic or perfectly inelastic collision, whatever, it doesn't matter. We'll talk about inelastic versus elastic collisions later. The change in momentum is actually relatively easy to calculate because you had speed, you had momentum, and now you don't. Right, you lose it. So if I, at about 100 I think latest tally, I'm like 92 kilograms. I'm just using 100 because I can do that math in my head. So we've got a person, right, who is going from an initial speed, an initial momentum of 30 meters per second, multiplied by their mass of 100 kilograms, to a new velocity of 0. So how much would your momentum change by? It would be a negative 3,000 units of momentum, a kilogram meter per second, right? So negative 3,000. That doesn't mean anything to you right now because it's a weird unit. You're like, 3,000 seems kind of big. $3,000 is a lot. I don't want to lose $3,000. I know that much, Mr. Willis. But here, let's put this into perspective. So, well, I'll get to perspective in a second. What that means is that if your change in momentum is that negative 3,000, then we can set this equal to your impulse, right? Impulses cause a change in momentum, or a change in momentum was caused by an impulse. So your impulse is also going to be negative 3,000 kilogram meter per second, which is a tremendous amount of impulse. The idea here is, this would be like having, literally 30 Mr. Willises jump on top of you simultaneously. That's not going to go well. So in order to not die in a car crash, you've got two options. And this is where this comes into play. This is why this is important, and this is what engineers get paid lots of money to do. You either have to be able to withstand a tremendous amount of force in a very short period of time, something that biologically really just doesn't work. The human body just doesn't withstand massive quantities of force in short periods of time. It doesn't go well biologically. At best, best case scenario, you're talking really bad bruises. Worst case scenarios, you're talking, ejected from cars or broken ribs or something worse. Or the other option you have, because that negative 3,000 is equal to a force multiplied by a time, either withstand 3,000 newtons of force in 1 second, or, which is 30 Mr. Willises, or extend that time of impact. If you can double your time of impact, you cut your amount of force in half, right? So if you go from, let's jot a couple of these numbers down, right? One option would be 3,000 newtons of force, 30 Mr. Willises, in 1 second. That would likely hurt you a lot. Or if you double this time of impact by wearing seatbelts or using an airbag or having a rubber padded dashboard, then you've cut that amount of force that you're feeling in half. And while 15 Mr. Willises is still a lot, it's a terrifying number, you have cut the amount of force that your body has to withstand in half. If you triple that, then you've cut it down by a third. Notice that all of these, when you multiply them together, still equal 3,000. And this is what engineers try to do. They try to extend the time of impact. And this is what your egg drop project really gets to. You try to extend the time of impact to make the force smaller and make it more survivable. That's the idea. Now, how does that play in real life? Where do we see this? Obviously, you've got things like airbags, seat belts. My grandfather, this is not my grandfather, this is just a meme of someone I found online because why not use it? Used to always say they don't make cars like they used to. You get in a little fender bender and you have to replace the whole bumper, or the headlight pops out, or there's thousands of dollars worth of damage and you're only going 15 miles an hour and everyone's angry and your insurance rates go up. The biggest complaint is that they don't make them like they used to. Yes, absolutely. And I will argue that that is because we have learned things, right? We have gotten better. Old styles of cars after an accident really didn't take a lot of damage. This is a good example of one. I took this photo personally after an accident on the interstate. It was northbound 57, 294. I don't know what it was. I think it was 294. It doesn't matter. This late 90s Nissan Frontier pickup truck did not actually experience a whole lot of force. Or sorry, not a whole lot of force. I don't want to say that. Didn't experience a lot of damage, right? They got rear-ended. What had actually happened was someone way up in front of us, there's a long line of cars, cut someone off, and everyone decided to slam on their brakes simultaneously. Well, I didn't think that I would have time, so I slammed on my brakes, sure, but I also swerved off, because I was in the left lane, far left lane, into that little shoulder where people can pull over. And I thought that combination of those two would just get me out of everyone's way and that'd be fine. Unfortunately, the Nissan did the exact same thing, and I still wound up hitting them. So this is what their back end of their truck wound up looking like. The back or front end of my car looked a lot different. This is the same accident. The same accident going from one place to another, or one car to another. This vehicle, my vehicle, was completely totaled. 100% totaled. You can see the airbags were deployed in the background. 100% gone, unsalvageable. They took it to a scrapyard and I never saw it again. But there's a reason this happened. This person wound up going to the hospital after the accident was done. They had some chest pains. They had a couple of fractured ribs and some pretty bad bruising across their chest. It wasn't great. It wasn't awful. They were fine. But they obviously were in a lot of pain for a little while, which really sucked, right? Felt awful for it. I went to go get a burger. I was fine. My airbag went off. Their airbag didn't go off, right? But I went to go get a burger. And it looks like my car experienced a lot more damage. The reason cars do this these days is because they are designed with these things called crumple zones. And this is what you need to do for your egg drop, right? That project that I'm going to talk about in a couple of days with you guys as of the recording of this video. By the time you get around to watching the video, I probably will have already talked about it. These crumple zones are designed to extend the time of impact, make the impact last longer, and it reduces the amount of force that the object would experience. Now, you still have the same change in speed. I was going 75, 80 miles an hour, and then by the end of the collision, I was at zero. There's nothing you can do about that. But if you extend the amount of time of impact, you're going to reduce the amount of force that you experience, right? You either take a large force over a short period of time, which is not good, or take a very small amount of force over a large period of time. There are more examples of this other than car crashes. That was just one I had really good photos of. Water balloon toss or an egg toss game that you might play at a picnic or a family gathering is another great example of this. The people who get further apart in that egg toss or water balloon toss sort of game, once they start catching it, they always start catching it all the way up out with outstretched arms. And then as they catch it, they cradle it and swing it back with them, right? Extending the time of impact, reducing the amount of force exerted on the water balloon or the egg, hopefully not breaking it. That's what the crumple zones in your car do. They extend the time of impact and reduce the force on you so that you don't break like the egg. And that's what I want you guys to be doing for the egg drop project, right? That's literally what your paragraph is going to be about. So it's kind of a reward for watching this up to this point. That's the crux of the egg drop project. Extend the time of impact, and your egg should survive. However you want to do that, extend the time of impact. So a couple more things. Collisions in general, we're going to talk about those because that's obviously a big part of this class. When you hit an object, you're going to give it some sort of speed. If it has velocity, it's got two things, one of which we'll talk about later. It's got momentum, which we're talking about now, but it's also going to have some measure of kinetic energy. I'm going to not touch on kinetic energy a lot. The book will talk about kinetic energy, and I bring it up now because I want you to gloss over that, right? We're not going to talk about kinetic energy yet. We'll talk about kinetic and potential in Unit 9. So we already know that if the ball rolls across the table and hits another ball, the second ball is going to move, right? We've all watched people play pool or billiards, whatever you want to call it, at some point. Or you've played bocce ball in your backyard, or seen those YouTube videos of people running at each other holding yoga balls and one small person goes flying in the other direction. It's the same idea. The idea behind this is actually our second style of equations for this class, for this unit, is conservation of momentum. Momentum is going to be conserved. Now, this isn't something that some nerd in his mom's basement pushing up his glasses on his nose decided should happen. This is just what we observe when two idiots run at each other with yoga balls in between them. And I say that knowing that I do that often. It's a lot of fun to watch my younger sibling go flying across the room. I enjoyed it thoroughly. But the point is, mathematically speaking, we observe momentum being conserved. Just like energy will be conserved in our next unit, or mass was conserved in chemistry last year, right? You didn't lose any atoms of hydrogen when you balanced those chemical equations. There was the same number of hydrogen atoms on the left as there was on the right. Momentum is also conserved before objects collide and after it collides. So basically all the momentum every object in the collision has before they hit each other is the same amount of total combined momentum that all the objects have afterwards. It might be redistributed between different objects, but the total is still the same. Why? I don't know. It's one of the things I'm going to ask whatever divine creator is responsible for all of this whenever my time comes, right? Thankfully, it wasn't on that interstate right there in those pictures. Anyways, so we can talk about baseball. Baseball is another really good example that doesn't involve car crashes. Which object has more mass? These aren't meant to be trick questions. I'm going to fly through them because you guys can read them and hopefully know the answers. Baseball bats are more massive than the balls themselves. Which one is moving with a greater velocity, though? When you're watching a pitcher throw a ball at a batter, the ball is moving with a greater velocity. The ball is moving, if it's a standard fastball for an MLB pitcher, 95 to 98 miles per hour. Some guys are hitting hundreds. That's awesome. But I'd say on average, 98 is a fairly conservative estimate. Baseball bat's not moving 98 miles an hour. They're swinging it pretty quick. Don't get me wrong, but 98's really fast. Anyways, so when the two objects collide, which experiences a greater force? I'm going to let this linger because all of you are going to give me either the bat or the ball because we forgot about last semester. Newton's third law. The forces are equal and opposite on each other. Always. The amount of force the ball feels is the exact same amount of force that the bat feels. In the same way that if I hit the wall hits me back with the same amount of force. Those two forces are always equal and opposite because they're the force that keep the bat from entering the ball, or the ball from entering the bat. The force of those electrons repelling one another. And they're always equal and opposite. It's just the way it is, right? It's just what we've observed. So if the forces are equal and opposite, then that means the impulses on both objects are the same as well. And if the impulses are the same as on each object as well, then the changes in momentum are the same. And this is definitely 100% a test question. If the forces on both objects when they collide are equal, like they were last semester, that means impulses are the same as well. So my car hit the car in front of me. Our impulses, the amount of force I put on him and he put on me, were equal. Our impulses were the same. Now, the forces in time were redistributed a little bit differently. Or sorry, the amount of time of collision were redistributed a little bit differently. But it's, impulses. They're going to be the same. All right, so there it is. This is the idea. This is actually the textbook definition for conservation momentum. If you want to jot it down, go for it. Otherwise, highlight it if you printed these out, because you can find the version I don't talk over on teams, like always. So the total momentum of both objects before they collide is equal to the total momentum of both objects after they collide. And we can rewrite this equation a multitude of ways. You could solve for the momentum of the bat first and then plug it in. Whatever you want to do. We're doing mass of that object multiplied by its initial speed, add it to everything else, set that equal to the mass of the initial object multiplied by its final speed, added to everything else's momentum. That's all it is. Two types of collisions. I'm going to keep this strictly at a vocab based sort of thing. We'll come back to this vocab when we talk about energy for sure. But we're not going to there's too much calculus involved in inelastic collisions. So for the sake of this class, we're going to have all of our collisions be elastic collisions, meaning there is absolutely no loss of energy. Now, I know I said that momentum and energy and mass and none of those things ever get lost. They don't actually get lost. They just go into other things, other forms of energy that we haven't talked about yet. And that's why we're ignoring them. We're not ignoring them because they get lost. And it's like when I lost the $50 that someone gave me for Christmas last year because my wife threw out a whole bunch of wrapping paper and tissue paper, and it was probably in like the tissue paper somewhere. I'm sure it's happened to you guys before as well. It's not lost like that. It goes somewhere. But we haven't talked about how much heat is generated when that metal bends and conforms and twists, or the light that could be emitted in terms of a spark, or the sound that was made in the collision between the two cars. All of those took energy to make. But we could include them in the calculation, but then I would have to teach you how to calculate quantities of heat or quantities of light or quantities of sound. And we'll get to light and sound later. We won't do heat. That's an honors thing. But we'll talk about light and sound later, just not yet. So know that everything we're doing, all that energy, all of that momentum is going to be converted from one object's velocity to another. In real life, nope. My car was in about 50,000 really small pieces all over the interstate. And each one of those had a fraction of the car's total momentum. But I would use a computer to calculate that. I wouldn't want to do that by hand. So nearly all collisions in real life are inelastic. They produce heat, they produce light, they produce sound. But in this class, we're going to ignore that because we haven't talked about those yet. That's the point. Anyways, so if all collisions are inelastic, why even discuss elastic ones? Again, we're sticking with those. So as far as we're concerned, hey, test question again. Look, that's a single sentence in red all by itself. We assume all collisions in this class are perfectly elastic. Definitely a test question. You are welcome. So what that means is that in momentum before and momentum after, we're only talking about changes in speed. We're not talking about debris, pieces breaking off, sound being generated, nothing. Strictly speed. So let's talk about it. This first example number 3, really easy if I'm being completely honest. To advance a runner on base, baseball players will often bunt the ball, right? Baseball or softball both will do this. So if you've got a 90-mile-an-hour fastball coming in, not very fast, sure, but if you've got a 90-mile-an-hour ball coming in, it's about 40 meters per second, and it hits a stationary, because they're bunting, 8-kilogram bat, and the ball bounces back into the field towards the pitcher, what is the speed of the 2-kilogram ball after it bounces backwards? Now, the couple of things I encourage you to do, and assignment 1, this is a problem on assignment 1, does include every now and then drawing a picture, because drawing that picture will help you organize the equation. It wasn't required before. It's still not required now, but now more than ever, I encourage you to draw a picture. Your picture doesn't have to be this great. I rated Google Clip Art, so I kind of cheated. Sorry. You've got the ball's initial velocity coming in, and then it hits the bat, turns around, goes the other way. So right off the bat, pun intended, right at the beginning of this problem, you recognize we have different directions. So we're probably going to need positive versus negative shenanigans in some form or fashion, right? Make a list of your variables. I like to organize these variables based on objects. So I'm going to stick with the bat. The bat had a mass of 8 kilograms. The bat had an initial velocity of 0. The bat has a final velocity of 0. The ball hits it, and it doesn't move, right? Let's assume the Incredible Hulk is holding this bat, and it's not going anywhere, as opposed to me, where it would definitely recoil a little bit, right? Especially post-surgery, Mr. Willis. It's a little soft on that right arm, and it makes me sad. One day they'll clear me to go back to the weight room. I think I'm actually only a month out. I'm excited. Anyways, so for the ball, The ball had a mass of 2 kilograms. It came in with a speed of 40 meters per second, and we want to know its final speed. This helps set up the equation. The equation is always momentum before they collide is equal to momentum after they collide. Notice here for our notes, I color-coded those suckers for you so that we can get an idea, right? Try to visualize how all this is going to work together. So if I wanted the momentum of both objects before they collide, I need the initial momentum of the bat added to the initial momentum of the ball. And if I want the total momentum afterwards, these two things don't stick together, right? They continue moving independently. Then I'm going to separately have the final momentum of the bat and the final momentum of the ball. So these two lines of math that I've got written over here in step 3, they're the same thing. I'm just getting more detailed and giving myself a place to organize and put things. That's all this is, and I understand it's one of the more confusing parts of this unit. But notice what it helped me do. The initial momentum of the bat was 0 because its velocity was 0, right? 8 multiplied by 0 is going to be 0. Same over here. The final velocity, the final momentum of that bat is still 0 because, check it out, it didn't speed up or slow down. It didn't change its motion. So the only thing that changed its motion here was the ball. And this is a really weird, not likely scenario because you'll notice that these are going to give you 2 multiplied by 40 is going to give you 80. Divided by 2 again is going to give you 40. If this is a perfectly elastic collision, the definition we just talked about, no energy is lost, no momentum is lost, nothing is lost. All of that speed is converted back into the ball because the bat didn't go anywhere. So, does this make sense? Sure, totally makes sense. The bat's stationary, all the momentum is returned to the ball, and we're good. It only happens in perfectly elastic collisions, and those don't exist in the real world. Yay, made up physics for high school. But that was it. So, moving on. Here's an example. Exact same scenario, but let's make it realistic. What happens if that bat recoils? What happens if it's an average person holding that bat for the bunt and the bat moves backwards just a little bit? Here's how that's going to change. Incoming ball, bat is stationary in terms of our initial set of stuff, right? The bat doesn't move. You're set, ready for the bunt. And then the ball is the only thing coming in. But let's say after the bat and the ball collide, the ball obviously rebounds, goes back towards the pitcher, but the bat also recoils. The bat moves backwards. That's going to change things. It doesn't change the setup, right? Notice I still make my list of variables for the bat. I still make my list of variables for the ball, and it doesn't change the equation I'm using or how I set it up, right? I've got a bat and a ball exclusively. They're both moving independently before the collision in red. They're both moving independently after the collision in blue. But after the collision, the ball's not the only thing moving anymore. And so you've got to change it. You've got to add this term. Now be very, very, very careful with our 8th grade algebra here. That 8 multiplied by 3 is going to give you 24. You should not ever, please, 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 with the love of all that is holy, do not combine 24 and 2. 2 is a multiple of that final velocity of the ball. We don't know what that is. It's an unknown. We could be adding 2 if that speed is 1 meter per second. We could be adding 4 if it's 2 meters per second. We could be adding 2,000 if it's 1,000 meters per second. I don't know what that term on the right is. So I have to move 24 first. Subtract 24 from both sides. Then you can divide by 2. Now, here's where you'd be able to notice if you had made a mistake there. Do a quick common sense check. If some of the momentum that the ball came into this collision with was given to the bat and caused the bat to move, then that means when it turns around and goes back towards the pitcher, it has lost momentum. It doesn't have all the original momentum it had. And if it has less momentum, it has less velocity. So your velocity returning to the pitcher should be less than 40 because some of that momentum was transferred to the bat. Now notice the bat didn't give you the missing, 12 meters per second, because the mass is 4 times larger in terms of mass. The bat is 4 times larger in mass than the ball is, which is why its speed is 1/4 of the difference, but that's neither here nor there. Just make sure it's smaller. That's the idea. So I'm going to do one more example with you guys, and then I think there's only like 2 left. That was the baseball one. I want to do one more with the cars where they stick together. Yeah, so 2 more slides, and then we're done. So example number 5, we've got 2 cars. One car, which is a mass of 1,750 kilograms, 1,750 kilograms, moving at 28 meters per second. Rear ends a smaller car, 1,025 kilograms. Both of those are masses. You've got 1 speed so far. And that other car was at rest. That tells you the velocity of the second car before they collide. Describe the velocity of the cars if they stick together after the collision. Okay, cool. Let's draw some pictures so that we can organize some stuff in our head, because being dyslexic, reading this is hard enough, but physics word problems, no one enjoys. I do, because they're a puzzle and I'm weird. Maybe that's why I do this, but that's not something the normal person likes. So let's draw a picture. We got 2 cars. My moving car I made green. My stationary car I made red, so that I could keep the 2 of them separate and distinct. You don't have to color code them yourselves. These are just tips that I think are helpful if you're getting stuck. So one car is moving prior to the collision. The other car is stationary. After they collide, they stick together and move together, right? The metal maybe locks each other up and they get entwined together and they move together as one solid object. Doesn't happen often, but it's not impossible. So let's make a list of our variables describing what it is we see. The green car has a mass of 1,750. Now, that's not going to change, right? I know in a real life, pieces will fall off. Your bumper will fall off. Your headlight will come out. There will be shards of glass and metal. I get it. We're not incorporating that, because then you need a computer to do the math for you. It's too much stuff to keep track of. I did that in college. It was not fun. So 1,750 is the mass of the green car. It was moving at 28 meters per second. I don't know what its final speed is going to be. It wasn't given. It was asked for, right? The final velocity of the cars. So the red car initially has a different mass, and it's moving with 0 meters per second worth of speed. It has no initial momentum. It's not going anywhere. It's sitting at a red light or a stop sign or whatever. It's not moving. Afterwards, it has some unknown velocity. I have to solve for it. The catch here, and this is the thing to remember, if they stick together, they travel with the exact same velocity. The only catch is that you have to combine their masses after they collide, because they move together, right? It's like if, I don't know, I'm riding my bike and all of a sudden my toddler decides she wants to hop on my bike with me. Now I've got to pull both of us, and I'm responsible for applying a force to move both of our combined masses. Same thing here, right? After the collision, they stick together, so you have to combine the masses. It's still the same starting equation. Momentum before is equal to momentum after. And before, we've got the green car and the red car moving separately, independently, which is why I separate them by a plus sign, right? That addition sign. They're moving independently. After they collide, notice I took G and R for green and red, and I just made it a subscript. They move together with one combined momentum. And so I can describe the momentum of the green car as its mass multiplied by its velocity. I could describe the momentum of the red car before they collide as its mass multiplied by its velocity of 0. No point in doing that, but I put it there as a placeholder so you know I didn't just ignore it. It happens to be 0. And then the combined masses, because they stuck together afterwards, are traveling at one combined speed. And that makes this a lot easier to solve. Right? So you find the initial momentum of the green car. It came into this with 49,000 units of momentum, kilogram meter per second, but 49,000. And the combined mass of both of them, if they stick together, is your 2775 kilograms. Divide. And what do you notice? Does this number make sense? Please do that at the end of all of these problems. It really does help. Does this number make sense? Yeah. If the red car was stopped and got hit, you're going to speed up. If the green car was moving quickly down the road and runs into something, you're going to slow down. Whatever velocity you calculated at the end of this problem had better be between 28 and 0. It's going to be some halfway point if the 2 cars are the exact same mass. If one's a lot more massive than the other, it won't be a halfway point, but it'll still be in between 28 and 0. So that was your last example problem. Now, one last thing I want to do with you guys. I'm not going to make you do this on the exam, but I think this is really cool. This is where Newton got his third law. He was working with impulses and momentums, and he actually didn't write the word accelerate in his book that he published at all, anywhere. It was all momentum and collisions where he got his 3 laws of motion. And this is what he did. So if using that accident from the previous slide, let's say this accident occurred for 0.3 seconds, right? Car accidents happen fast once you make contact. Who experiences a larger force? This is something that he did. His 3rd law says that they should be the same. So which one is it going to be? I'm going to use numbers strictly from the green car and then separately numbers strictly from the red car. And I'm going to show you that they are the exact same thing. So if I wanted to calculate the impulse of the green car, it's your change in momentum, all right? Final momentum minus initial momentum. The green car had 28 meters per second of velocity initially, and after it collided, its speed went down, right? It slowed down. So that's our value for our amount of impulse. That's our change in momentum. The red car, same setup, totally different numbers. Notice I've got 1,025 because initially this car was at rest, and I've got my new mass of 1,025 and its speed. They're moving at the same speed because they lock together, but notice, if you don't believe me, type it into your calculator. The large green car that was moving fast lost 1,800 units of momentum, and the small red car gained 1,800 units of momentum. The impulses are equal and opposite, and if Newton's 3rd law was accurate, those forces wind up also being equal and opposite. And that's where he got these. I'm not going to ask you to do this proof with me later, but this is why I always come back to Newton's 3rd law in this unit, and I will do so time and time again. Forces on each other in a collision are the same, and that means your changes in momentum are the equal and opposite, and that means your impulses are equal and opposite, and none of this has changed. We're just adding in momentum and impulse. Those are 2 new vocab terms, but the overarching concept has not deviated, has not changed. So I'm going to leave you with that. I do want you guys to give a shot to the last 2 problems on there. Keep track of when things are moving and when things are not moving. That's really all I've got to say, right? Both of those, the last 2, they're not moving initially, neither object. So give them a shot. Watch out for kilograms versus grams in number 7. But, you know, you've got the work, you've got the answers. Please reach out and ask me some questions. When we meet in class, the 2 things that we will do that first day back is introduce things for our new students, obviously, get them accustomed to some stuff. Talk about course selection for your senior year. No idea what senior year is going to look like. Hopefully it looks a lot more normal with this vaccine rollout. We'll see. And then also talk about the egg drop project. Those are the 2 things we'll be talking about, which is why I made this. So if you stuck around, then you're welcome for the homework answers, and I hope it helped. Otherwise, please let me know how I can help. That's all I want. Thanks. See you guys.